Hello everybody and welcome to the NPTEL online certification course on semiconductor devices for next generation field effect transistors, physics perspective. This is lecture number 3 in the series of this course, and we will be today dealing with energy band diagram part 2 and introduction to MOS devices. So, we have learned in our previous discussions that the effective the thickness of the oxide layer, right, the oxide across the oxide, the potential drop is given as minus Q0 prime by Cox prime, where Q0 prime is the charge per unit area and Cox prime is capacitance, oxide capacitance per unit area. And this was the potential drop across the oxide layer which we were expected to see. Now, so typically therefore, you have two components which we have studied till now. One is your phi ms, which is the metal semiconductor work function difference, and we will also have another component which is this one, minus Q0 prime by Cox prime. So, if you want to add these two together, what I get is I get flat band voltage VFB is defined as phi of ms minus Q0 prime by Cox prime, right. So, the first component on the right hand side is primarily because of the difference in the contact potential between metal and semiconductor, and the second one is primarily due to the parasitic effects of 3 or 4 types of charges which are sitting inside the oxide layer, right, and they tend to sort of degrade your flat band voltage. So, what will happen therefore is that an external voltage source VFB has to be given so that you reach the flat band, right. That is the basic idea which we look into now. Now, let us come to the understanding of what are the various. So, when you go from gate to the substrate, what potentials do you encounter and which of the potentials will change if you apply a bias. So, let us study that and then we will go for the next stage of learning. So, let us look at it in this manner, that if we do, so if you look at, let me draw a diagram for you and let me show it to you, that let us suppose I have this MOS device structure here and this is my metal here, and then I have an oxide layer followed by semiconductor. So, this is the semiconductor bulk which I am talking about, and I have these positive charges, let us suppose, being inculcated near the oxide layer, and there are positive charges in boxes shown as traps which are inculcated near the silicon dioxide interface, right. We will go one by one and explain to you how these diagrams or how these are important to us. So, what we do, we have this gate terminal here, we have this bulk terminal here, and we just connect these two together through a gate to bulk potential VGB. Let me name it as VGB, right. And so, this is your gate charge QG, let us suppose, right, and you will have here the oxide trap charges, this is Q0 prime, right, and there will be also the charge here QC, which is basically the channel charge. Now, if you take this into consideration and write down an expression, I can write down VGB, which is gate to bulk, can be written as Cox, the drop across the oxide layer, plus the surface potential plus the phi ms, right, where Cox is the oxide. So, this is the drop across the oxide layer, psi s is the potential at this particular point, and phi ms is because of the metal work function difference, you will have a phi ms plot. Now, with this basic background which basically solves the Kirchhoff's law only, if I try to plot here the value of this. So, please understand, on the x axis you have potential, right, and on this axis you have the dimension, which is this dimension, y dimension, which you see. So, let me go one by one and explain to you. This is my bulk here, right, this is my bulk. So, this is bulk is either p type semiconductor or an n type semiconductor, and this bulk will give rise to your constant voltages, obviously, because bulk is, let us suppose, given a negative potential, and therefore, the potential will be very small at this thing, almost constant. Suddenly, as you leave the bulk, you will actually see a sudden rise in the potential. Why? Because now as you move up, obviously the potential will go on rising, because the gate potential has been given a larger value as compared to the bulk potential, and therefore this will rise. And then suddenly what happens is that there will be a sudden increase in the voltage here, right, almost a big drop. Now from so let me change it. So till this much point you will have you will see a extension which you will see till the interface, oxide interface, right, oxide semiconductor interface. After this, if you follow this curve here, right, then this will be almost like this. So across the oxide layer there will be some potential drop which will be equals to the oxide layer. So this and this is what the potential V with respect to y. If this direction is y, then psi of y is the variation of potential as you move from the bulk toward the semiconductor, right. And this this potential which you see here, this potential, right, this potential which you see here, because once it reaches the edge, it will again go on rising. Why? Because it sees a metal at the top, right, and therefore we define this to be as my VGB, gate to bulk. This is my gate to bulk. So this all gate to bulk is now being divided into three parts. The first part is basically my, so let me draw from here one line. This is your psi, this is your surface potential psi of S. Then this from here to here is your psi of OX, right, and this is your phi ms, metal work function difference. You understand? So this is your metal work function difference, the minimum of it, and then you have the surface potential, and then you have the oxide potential, the drop across the oxide layer is been shown here. So I get VGB equals to psi S psi ox plus psi S plus phi ms, right, that is what you get. Now let us suppose I make a change in the value of VGB, which means that I give a delta VGB change. So let me do that and show it to you. So I get a delta VGB change here. This will be delta psi ox plus delta psi S, and you can understand the reason why. The reason is any gate voltage change which you make, gate to bulk voltage change which you make, will finally get reflected onto the change in the oxide and the surface potential, because phi ms is almost constant, because once you have fixed the metal and the semiconductor, the phi ms value depends only on the contact potential of these two. So basically I can safely say that my del of phi ms, right, is always equals to 0. There will be no change once you have fixed the metal, and the semiconductor. Once you have done that, there will be no change. So any gate voltage change will be accommodated by the change in the oxide and the surface potential. That is one important point which you should always be careful about. Now since I have applied a potential, I would expect to see that the total charge neutrality should be still maintained, taking into account the VGB, right. And so this brings to our single point conclusion. The takeaway from all this discussion is that, look at the right hand slide, and this is the one slide which I want you to refer, and that will be your important slide before we shift topics, that the surface potential is a rising potential as you move from the bulk towards the surface, if you go ahead and do it. So this is a rising potential which will happen as you reach the silicon dioxide interface. It is its maximum. Within the oxide layer you will see if not that rapid rise, but a small rise in the voltage, and that is psi OX, quite a large substantial amount, because that is an oxide layer. Subsequent to that you will again see a rise, because it should reach the metal work function or the metal potential, right. So and any potential I am giving on the gate voltage will be substantiated by the oxide change and the surface potential change. With this we have also understood the basic fundamental principles of the flat band and the fundamental principle of the charges. This will be useful when we do the Fermi level or the energy band diagram. Let me come to the MOS, basic electrical properties of MOS device, and that will be quite interesting or useful to all of you. Two things which is important, and let us go basic. Let me give you a basic mass law action, and I assume that you will be understanding this. To refer, please go to some other NPTEL course or from a basic book, and I am keeping it to the bare basics so that you are actually initiated to the subject. There is a mass law action which happens in any MOS device, and that is referred to as Np is equals to Ni square, which is written here. What does it mean is that the equilibrium concentration of the mobile charge carriers in the semiconductor will always follow the mass law action, which means that the product of the electrons, free electrons and holes will always be equal to the square of the intrinsic carrier concentration, right. So, you see N into P is equal to Ni square, primarily meaning that N will be approximately equals to Ni square by P, or P can be written approximately equals to Ni square by N, right. Now, N and P obviously denote the mobile carrier concentration of electrons and holes. Now, let us take an N type semiconductor. In an N type semiconductor, P will be obviously the minority current carriers and electrons will be majority current carriers. So, what happens therefore is, if you place the minority current carriers P here, which is a very small quantity, obviously your N will be very large, and vice versa when you take a P type semiconductor. So, this is for a P type semiconductor, you want to find out the majority current carriers, and this is for an N type semiconductor where you find it for the electron as the majority current carrier. The intrinsic carrier concentration at 300 Kelvin is given by 1.45 into 10 to the power 10 per centimeter cube. Now, if you assume that you dope it with a third group element, which is an acceptor ion Na, then obviously I will get my number of holes will be equal to the concentration of the acceptor ion. If I assume 100% ionization, primarily meaning what? That all the Na particles which you have inserted from outside are contributing to one hole, then we define that to be as a 100% ionization. So, what is a 100% ionization? Let me explain to you once again. 100% ionization primarily means that each Na will contribute one hole to the system. So, if you have inserted 100 boron atoms per centimeter cube, then you will get 100 holes per centimeter cube in that domain, right. Now, if this is true, let us come to the last statement of this slide, which tells me that Np0 is equals to Ni square by Na, which means that Np0 is basically the minority charge concentration if it is a P type element, and if I assume 100%, then all my Na will be equals to P, and therefore, if you look at this expression here, I am replacing P by Na. So, what I get is Np0 equals to Ni square by Na, right, and this is what you get to Ni square by Na, where Na is the acceptor charge concentration. So, this is the number of electrons which you get, and the number of holes which you will get will be approximately equals to Nd in this case, right, and that will be giving you a value of number of holes in the P type semiconductor will give you the value here. This gives you a brief background about the MOS electrical characteristics. Now, let me come to the fundamental principle based on which we will be studying the energy band diagram, which you will be studying in some other course. I will just give you a precursor to that. Now, if you take a silicon is basically a catenated material, which means that silicons each bonding will be surrounded by 4 bond here, 1, 2, 3, 4 bonds. So, silicon is a group 4 element and this 4 bonding will be there. Once you dope it with an external element, say phosphorus, which is a group 5 element, then what it does is it remove one of the silicon, place itself there, and it combines with the nearest silicon neighbor, but then it has one extra electron which it leaves apart. And if there are 100 such phosphorus atoms per centimeter cube, you will have 100 such number of electrons being also introduced, right. And this is what is known as silicon doped with phosphorus atom. Now, how does it influence our energy band diagram? You all are aware that energy band diagram will have a conduction band, a valence band, right, and an intrinsic Fermi level. Now, you might have also known that a Fermi level is a place where the probability of finding electron at 0 Kelvin is half, right, which is somewhere in the middle. So, if you look at the intrinsic Fermi level, it will be somewhere in the middle, it will be forming an intrinsic Fermi level. Now, conduction band and above, conduction band is the state which will have, if you, so look at a very important point on the y axis, it is energy, electron energy. So, you see the conduction band edge will have the minimum electron energy. Any free electron will have minimum energy at the conduction band. and therefore the edge of the conduction band is the most stable part of any design of any semiconductor in terms of any electron, free electron. Why? Because the energies are minimum. When the energy is minimum, that is where the electron will like to sit, right. So this is, but as you give more and more energy, let us say through optical domain or through biases, the electron energy will go high and the electron will be shifted higher and higher in the conduction band, right. And when you remove the energy, they will dissipate the energy to the lattice and come back to again to the edge of the conduction band. This is what we have learned. Second thing is, in the valence band, if you look, there are no free electrons, right. To generate free electrons, you have to give an energy equal to this band gap, which is EC minus EV. This is your band gap here, which energy you have to give from an external source for any electron to jump from the valence band to the conduction band, where it will be treated as a free electron. Now, with this basic statement clear to you, let us introduce a phosphorus level in the energy level diagram. Now, phosphorus is basically a one which is contributing an electron, right. So, the donor level ED, which you see in this diagram, this one is very close to the conduction band. So, look it from the energetic point of view, not from the space point of view. If you place a level very close to the conduction band, the amount of energy required for that band to give free electron to conduction band will be relatively very small. You do not have to give an energy equal to Eg, which is the band gap, in order to shift an electron. You have to give an energy which is maybe 1/10 or 1/15 of that energy, which will be very, very small. So, the phosphorus energy or the phosphorus energy is somewhere lying in this region. This is the discrete band which is there lying in the phosphorus atom. I hope it is clear to you in this case. So, let me give you a reverse statement and explain to you what will happen if you had doped with boron atom. If you are doped with boron atom, then this phosphorus will be replaced by boron, but boron has only three bonds because it is a group 3 element. It will do what? It will make a connection with these 3 silicon, but with this there will be a hole available. Why? Because there is no bond formation taking place between them, and therefore it will be forming a hole there, right. So, any boron which you insert will introduce a hole. Assuming again 100% ionization, the boron or the acceptor level, energy level, will be very close to the valence band. So, the acceptor level will be very close to the valence band. This is EA or acceptor level. We would also write it as E small a bottom line, which means that, so if you want to generate a hole, you just have to shift it from the valence band to this particular point, which is also very, very small as compared to Eg. Once you do that, you have a hole available here, right. So, what does donor level do? Donor level gives an electron and itself converts into a positively charged, and that is the reason you see it is positively charged here, right, and it is negatively charged here. What about boron or group 3 element? It itself gives a hole, itself becomes a negative charged particle. So, what will happen is it will accept an electron from there, right. So, this will become negative in nature and they will become holes here. So, it will be positive in nature, and these are all free charge carriers which will be available, correct. So, this is the basic understanding of the energy level which you see. Keep that into your mind and we will go step by step now to build up the energy level diagram. Look at the right hand side corner on the diagram, and what we have done is that we have introduced a positive bias to the gate side of a MOS device. This is your metal, right, this is your metal, and this is the metal. There is an oxide layer and this is the semiconductor. This is the semiconductor, this is the oxide layer. I have slightly sort of enhanced the image, right, and we have taken it. So, any positive voltage you give on the gate side, it will generate an electric field down below, and therefore, if you have a p type substrate on the semiconductor, the holes will be thrown inside the substrate. So, that is the reason you see the holes arrowhead is showing in this direction. Why? Because I have given a positive voltage on the gate side. When I give a positive voltage on the gate side, there is electric field working downwards. As the electric field is working downwards, the holes will be pushed downwards. When the holes will be pushed downwards, you will have minority current carriers electrons sticking to the silicon dioxide interface, right. Let us take that picture which you see on the left hand side and place it on the right hand side picture. the knowledge which you have gained. When you put a positive bias here, you see you will be inducing a space charge region. The blue colored is the space charge region. Why there will be a space charge region? Because see, what will happen initially is, as you give the positive bias, you are pushing away the holes, right. Once you push away the holes, the shaded region will be devoid of any free charge carriers. There will be no free charge carriers here. There will be no free charge carriers. Why? Because you have pushed the holes away from the interface, silicon dioxide interface, and since you have not applied any bias on the drain and source, in fact there is no discussion on source and drain. So, there are no horizontal electric field, there is only lateral electric field or vertical electric field. So, what we are saying is there is a presence of vertical electric field, and the horizontal electric field is not present, correct, is not present, obviously it is not present, and that is the reason you will get a depletion charge here. And higher the p type doping concentration of the substrate is, lower will be the value of your depletion charge. So, you see xd which you see here, xd is the thickness of the depletion layer. If your doping concentration would have been very large in a p type semiconductor, this xd will be as small as possible, right. But if the p type doping is very small, xd will be relatively large. Please try to find out what is the reason for that from any standard textbooks or any other NPTEL lecture, right. Why is it like that? This comes the first step, that the first step is to remove the free charge carriers from the silicon dioxide interface, and a depletion region is formed, which I have shown here, right. This is also known as the space charge region. More is the value of your voltage, more will be the thickness of your depletion, because you are reverse biasing in a sense the depletion thickness, right. And as a result, what will happen? The depletion thickness will become higher and higher. With this knowledge or with this concept, let me frame a question for you, think about it later on. The question is, if I would have replaced this p type, right, by an n type semiconductor and applied a positive bias, then what would have happened, right. Think about it, and we can discuss this later on as we move along. But this is the basic MOS capacitor. Why? Because you have a metal oxide semiconductor and I have applied a bias here. Now, once we have done that, let us correlate the bias with the band diagram and the flat band. So, we have already studied the flat band, we have already discussed the bias conditions. We will now come to the condition where we will have a zero bias, a positive bias and a negative bias on a basic MOS capacitor structure. If you so look at it, this has been, so look at this structure, right. This is the MOS and this has been shifted in this domain. So, you see this gate is available on this side, and then you have an oxide layer, and then you have a semiconductor. So, this is the p type semiconductor which you see. Since your semiconductor is p type, I would expect that my Fermi level EF will be close to the valence band, right. If it would have been an n type semiconductor, my Fermi level would have been close to the conduction band. Obviously, the intrinsic Fermi level will be somewhere in the middle or at the middle of that junction. Now, when you apply a zero gate voltage or a zero bias, there will be no bending of the bands, and that is correct also. Why? Because the bending of the band takes place by virtue of this Q into V, energy is equals to Q into V, right. When you apply a voltage and you multiply with Q, you get energy in terms of this. But if your V is equals to 0, obviously E will be 0, and when E is equals to 0, it will be all straight line aligned, as you can see in this side. This is a very straightforward way of looking at it. Let us first apply a positive bias, right. We apply a positive bias on the gate side. When you apply a positive bias on the gate side, you are effectively looking into the fact that on the p type substrate you will have a negative bias, or negative charges will be accumulated by the concept of neutrality. Once you do that, since the energy levels have actually gone down, because it is minus Q times V, because it is electron, you see the bands are bending downwards near the oxide layer, and you can see the conduction band has bent downwards, the intrinsic Fermi level has bent downwards, and the EV is also bent downwards, right. And effectively therefore, if you look very closely, now near the interface, which is the silicon dioxide interface, this one, your Fermi level is slightly closer to the conduction band and slightly away from the valence band. Interesting to see, the Fermi level does not change, it is still the straight one. Think about it, why is it like that, right? I will not discuss that in the class here. The intrinsic Fermi level, the conduction band, the valence band and the Fermi level will all dip downwards. The reverse will be true when you apply a negative bias. When you apply a negative bias, there will be positive charges, accumulation of hole near the interface, right. This one is basically your depletion region, this one. This typically is a depletion region, XD. Similarly, yes, so this is your depletion region. Since holes are getting accumulated, charges are increasing, Q into V is larger and the band tend to move upward in this case. Now you see, very interesting, the same logic which I discussed to you in the positive bias, you have the same logic here. Because of the positive charges near the interface, the valence band is becoming very close to the EF, right. I will just rub this here and then you see, look, just concentrate here. If we concentrate here, the light dashed blue curve line, straight line is now very close to the black line of the valence band, which means that the valence band is relatively closer to the Fermi level, assuming therefore I have large number of free charge carriers being developed in this case. Okay. So this is the basic MOS capacitor and energy band diagram which you see. We have understood the depletion region, so let us have a sort of a methodology which will give me a brief idea about XD or the depletion width. Just to keep in mind, the depletion width is given by this, where phi s is the surface potential, right. We have already discussed this potential phi s. Now you see, let us look at the right hand side diagram and I will correlate that with the depletion thickness. Look at the right hand side diagram. This is bending downwards. Bending downwards, please remember, which means that what voltage we have given. Look at the, if you look at the previous slide, bending downwards primarily meaning I have applied a positive gate bias, right. So I have applied a positive gate bias here, positive gate bias, and I have got a negative side here, right. These are, and in this depletion region there will be immobile charge carriers, So there will be no mobile charge carriers and so this will be having that value here. Now what has happened is, as you apply a positive gate bias, the conduction band edge goes down, the intrinsic Fermi goes down and the valence band goes down, and the distance between the interface and the point from which it starts to go down, that is defined as my depletion width. Why? Because beyond depletion width you enter into a region where the potentials are again constant. The effect of the potential on the gate side gets nullified beyond the depletion width. Till the depletion width you have a variation, beyond depletion width it is almost the straight line, right. And that is the reason you see EC, EFI, EF and EV are all straight line beyond the depletion width. It is given by 2 epsilon silicon phi s upon Q times Na, where Na is the acceptor ion concentration and phi s is the surface potential. Now this is an interesting one. How do you measure the surface potential, right? You measure the surface potential by seeing the difference between the intrinsic Fermi level between the, so let me rub this so that it is clear to you. So how do you define the intrinsic Fermi level? You define the intrinsic surface potential as the amount by which either the conduction band or the intrinsic Fermi level has gone down by application of a external potential. That is defined as my surface potential, or the potential which is available at the surface of the silicon dioxide is referred to as the surface potential, right. And that is given by phi s here. So just place the value of phi s in this expression and square root of that is xd, which means, this is quite interesting, that phi s, so xd or the thickness of the depletion is basically dependent on the square root of phi s. So it is not linearly dependent, it is dependent as square root. So it is a parabolic dependence will be there, right, and that is quite interesting in this case. We define another term which is basically the potential phi Q phi p or E phi p, and is given as thermal voltage VTH, which is 26 millivolts at 300 Kelvin, ln of natural log of Na by Ni, and this is known as phi p, and explain to you another way later on, but that is what is the value of phi p, right. So this in an extent gives me an idea about the depletion layer thickness here, and we also look at the surface charge density, right, which means that can we predict the electron concentration which is there in the conduction band by looking at the difference between the intrinsic Fermi level and the Fermi level. So you see it is given by this form, that n is equals to Ni exponential Ef minus Efi. If this difference is larger, which means that the Fermi level has actually shifted towards the conduction band more, the difference will be larger, and therefore my electron concentration will be larger, which means that if my Fermi level is closer to the conduction band, more is the concentration of electron. If my Fermi level is closer to the valence band, then more is the concentration of my holes, right. So this is for the n type semiconductor, which you see for if you take a p type semiconductor substrate, the electron inversion layer is given by this formula. You do not have to worry from where we are getting it at this stage, but just keep in mind that it depends upon the value of the phi fp here, which we have already defined, plus delta phi s. How much delta phi s are you doing? So phi fp is the absolute value, plus delta phi s is the change in the surface potential by virtue of an external voltage, right, or external bias, and Vt is the thermal voltage which you see. This is known as the surface charge density which you see. How they are actually formed? We already know how these are formed. So if you have discrete atoms very far off and you try to bring them closer and closer, the band formation takes place, right. I would request you to study good books on, there is a good book which is source is given as Niemann here. Have a look at Niemann, or even Streetman and Banerjee is a nice book to discuss all these basic concepts of energy level and energy band diagram, right. But the basic concept is when the two atoms are very far apart, they will not interact, they are isolated. When you start bringing them closer, the discrete energy level tends to interact with each other, and now you have bands formation taking place. So you have an energy band, conduction band, valence band, and the gap for me, this band gap available to you. So this gives me a basic idea of the formation of the energy gap. We will take this up in the subsequent part of it. Thank you.